Hello and welcome to the 22nd session of the Introductory Biostatistics Distance Learning course. In the previous lecture, we introduced the concept of linear regression, and we concluded with these two questions. The first was, we had gotten estimates of the intercept and slope, beta 0 and beta 1 respectively, and we wanted to ask the question, is beta 1 significantly different than 0? Which is basically how we've always progressed. We first get an estimate, and then our next question is that significantly different from 0? Then our second question was, anytime we have a parametric procedure, it has a parametric statistical procedure, such as linear regression, it has certain assumptions, and in order for the results to be meaningful, the assumptions of our statistical procedure need to have been met. So, have the assumptions of regression been met in our example? So let's address this first question about is beta 1 significantly different from 0? And you'll remember we were looking at the relationship between BPF and age, okay? And so beta 1 in this example, beta 1 hat, was telling us how a 1-year increase in age affects the mean BPF, okay? All right, so in order to determine if beta 1 is significantly different than 0, we need an estimate of the variance of beta 1, okay? So what does that look like? And again, we leave the derivation of these things to the statisticians, but we can use the results in order to provide us with some insight. Okay, so here's the standard error of beta 0. Remember, this is the intercept, the y-intercept. Okay, and the equation looks like this. And then the corresponding equation for beta 1 is here, okay? And both of these terms involve this term s sub y given x, and that is equal to the residual variance in y after accounting for x. And this is sometimes called the standard deviation from regression. It's sometimes called the root mean squared error. But here we use this notation s sub y given x. Okay? And so now, given these equations, one is the standard error of the intercept, and the other the standard error of the slope, we can construct test statistics in order to answer this question, is it significantly different from 0? Okay? So, test statistics. Okay? So, both of these regression coefficients, we use a t-statistic to test any of these hypotheses we're interested in, and each has n-2 degrees of freedom. Okay? That's the sample size number, the sample size subtracting the number of parameters estimated. Here we have beta 0 and beta 1, so that's why we have n-2 degrees of freedom. Okay? All right. So we can construct test statistics for both of them, and typically we're only interested in test statistics involving the slope. Here's the test statistic involving the intercept, but typically we're only interested in test statistics involving the slope. Okay, so you'll see they take a very familiar format, and they're analogous to each other. Okay, so we take our estimate minus the hypothesized value divided by the standard error, okay? And typically here, for the slope, the hypothesized value is going to be 0. We're going to be interested in determining whether beta 1 is significantly different from 0, or the alternative is that it's not equal to 0. Okay? Alright, so now that we have an estimate of the standard error, we can go through our 7 steps of hypothesis testing. And as I mentioned, we're typically interested in hypotheses involving the slope, not the intercept. Okay, so let's go through our 7 steps. So our null again is going to be that beta 1 is equal to 0. The alternative is that beta 1 is not equal to 0. Type of data that we're working with is a continuous outcome and a continuous covariate. The outcome is BPF. The covariate is age. We're going to fit a linear regression. The test statistic, remember, is a t. So these we can do without stata. And then with stata, we get this t statistic of 3.67 with 27 degrees of freedom. The p-value is equal to 0.001. We compare 0.001 to 0.05. Since it's less than 0.05, we reject the null. And then we conclude that there is a significant association between BPF and age. And we don't want to stop there. We want to say specifically, it appears that as age goes up, BPF goes down. And we knew that because the coefficient for age was negative. Okay? So what does that look like in stata? Okay, so the command is regress, the outcome is BPF, the covariate is age, the estimated slope, if we go here next to age, the coefficient, the estimated slope is negative 0.0028, and again there's the negative we were talking about. The estimated intercept, stata calls it the constant, is 0.957. And then the p-value for the slope is 0.001. And you can see that corresponding to that p-value, the null value of 0 is not in there. So 0 is not in that confidence interval. And we knew that because the p-value is less than 0.05. So we conclude that there is a significant association, and that for increases in age, BPF goes down. Okay? So you'll notice there's also, we can compare this to correlation. Remember, we said we can use correlation when we have a continuous outcome and a continuous covariate, which we have here. So we can see how this compares to the relationship we had when we used correlation to look at these examples. Specifically, here's the method that we used, and you'll see that the p-values are the same. They're equal. Okay, we got the exact same p-value when we did correlation as when we did linear regression. Our conclusions were the same. okay? And this isn't a coincidence, but this has something to do with the relationship between correlation and linear regression. And we're going to talk more about this in the future, okay? In fact, there's a simple formula for the relationship between correlation and the regression coefficient. So namely R, which is the correlation coefficient, is equal to beta 1 times S sub y over S sub x. And these things are all available in the Stata output. And so if you just plug this in, it's negative 0.00288 times 9.78 over 0.00488, which is equal to negative 0.577. And that was the exact same estimate that we had when we looked at the Pearson's correlation coefficient. Okay? All right. So if I can show you the, so that's a good thing. Basically, we're seeing that regression is a generalization of a lot of things we've seen. Regression is a generalization of correlation, and then in a future lecture, we'll see how regression is a generalization of the t-test, which we learned way back when. Okay, so if we look again at our Stata output that we had before here, you'll see that Stata also provides a test statistic and a p-value for the intercept. Remember, we said the intercept is under this thing called the constant, and here's the p-value, 0.000, very, very small, and obviously the confidence interval does not contain 0. Okay, so this is testing the null hypothesis. Is beta 0 equal to 0? Okay, but this is often not of interest, because here in this case, this corresponds to testing whether BPF is equal to 0 at age 0. Okay, that doesn't make any sense here, right? Because BPF can't be 0 at age 0, so this test is not really of interest. Okay, so we just want to make it clear what this is doing and why we typically focus on hypothesis testing on the slope. Okay. One thing some statisticians like to do is center the covariates so that this constant is more meaningful. And what do we mean by that? Instead of, if we had, in a typical data set, we would have BPF and age, and here would be, patient 1, 2, 3, 4, they'd have some number A, some number B, and so on. Somebody might instead say, let me take the mean age and subtract, I'm going to call it mean age bar, and instead plug in the mean age, okay? And so in that case, this constant, instead of having the interpretation as the mean BPF when age is equal to 0, it would have the interpretation as the mean BPF when age is equal to whatever the mean value of age is in this data set. Okay, so that's kind of a little bit more of a helpful interpretation, which some people prefer. That's called centering the covariate. Whoops. Which is when you subtract its mean. Okay, so now that we've addressed the first remaining question that we had about whether the slope was significantly different from 0, let's get to the second question that we had about whether the assumptions of linear regression had been met. Okay. So the assumptions of linear regression. There are 4 key assumptions. The first one is independence. Okay, what do we mean by that? We mean that, for example, my age and BPF will not impact your age and BPF. Okay, so that's independence. An example where this might be violated is if we have repeated measurements on the same subject. So if you measure my age in BPF today and you measure my age in BPF in a year, we obviously expect those to be highly correlated because they're measurements on the same subject. Okay? So if we have that, we have these things called longitudinal data methods to take the repeated measurements into account. A second assumption is linearity. Okay? So we assume that there's a linear relationship, a line, between the outcome and the predictors. A third assumption is called homoscedasticity. Of the residuals. Remember, the residuals are the distance between the actual points that we collect, the data that we collect, and the fitted regression line. And then homoscedasticity means that the residuals have the same variance. Okay? That means these E sub i's have the same variance. Okay? And finally, the fourth assumption is that of normality of the residuals. Okay? So that the residuals, E sub I, are normally distributed, the mean of 0, and some standard deviation. Okay? So you can see by writing this one equation, I've basically summarized assumption 3 and assumption 4. Because assumption 4 says they're normally distributed, and assumption 3 says that they have the same variance. Okay? All right. So let's take a look at these different assumptions. There's not much to say about independence. Independence, you just have to say that, hey, we don't have any sort of dependence structure, which we mentioned could be repeated measurements on the same subject, or maybe you have measurements on people in the same family, which you expect to be more similar than people in different families, for example. Okay, so independence, you just have to be kind of assess just by thinking through it and whether you think there should be any dependent structure in the data. Okay, so linearity is we basically think that the expected value of y given x, the covariate, is equal to beta 0 plus beta 1x. Right? That's a line. You know, something like this. Okay? Okay? So that might not always be the case, but for now we're assuming linearity. Okay? And then we have this the other two were the normality and homoscedasticity. Okay? And that's related to the residuals. Okay? So homoscedasticity says the variance of y given x is the same for all values, and normality says the distribution of the residuals is normal. So let's take a look at a picture to help us understand that. So here's our fitted regression line, the black line, and normality and homoscedasticity says that the residuals, the actual points, so given a value of x, here, for example, the residuals are going to have this normal distribution that has the same variance at every value of x. Okay? So like here's x, some x1 value, some x2 value, and some x3 value, and they're all normal, and they all have the same variance, okay? Those are the residuals. Remember, the residual, so if I had a data point here, the residual would be this distance here, okay? So the distribution of those is normal with the same variance, okay? That's normality and homoscedasticity. And we're going to talk a lot more about assessing these assumptions in the next lecture, okay? So now let's talk about confidence intervals. Remember, we're most interested in the slope, beta 1, okay? So we can construct confidence intervals for these regression coefficients using our t-distribution, okay? So what does it look like? Well, it's going to take that familiar form we're always interested in. The estimate minus critical value times standard error, comma, the estimate plus the critical value times the standard error. So let's just write that out. Here it is. Our estimate minus the critical value times the standard error, comma, the estimate plus, the estimate plus critical value times standard error, okay? And the confidence interval is interpreted just as we've seen before, okay? And so remember, we always know about the duality between the confidence interval and hypothesis testing. So if we have a confidence interval, we can complete our 7 steps of hypothesis testing. So again, our null is going to be that beta 1 is equal to 0. The alternative is that it's not equal to 0. Type of data that we have is a continuous outcome, which is BPF, and a continuous covariate, which is age. We're going to do linear regression to assess this relationship. Those are my steps without stata. Then stata tells me that the estimated beta 1 hat is equal to negative 0.0029, and that the 95% confidence interval. So here, remember in step 5, we usually look at the p-value, but again, there's this duality between the p-value and the 95% confidence interval. The 95% confidence interval goes from 0.0045 to negative 0.0013. And so what's important about this 95% confidence interval? This side is negative, this side is negative, and so 0 is not in here, okay? And so since the confidence interval does not contain 0, 95% CI does not, just erase this, does not contain 0, we reject the null. And in step 7, we say, we conclude there, based on our sample, we conclude there is a significant relationship or association between age and BPF. And obviously we wouldn't stop there. We would say that as age goes up, BPF goes down on average. Okay, so what does this look like in stata? Here we go. So regress, BPF, age. Here's the slope. Here's the intercept. And then here's the 95% confidence interval for the slope and for the intercept, okay? And we can see, since neither of them contain 0, we know that both of these p-values are going to be less than 0.05. Okay. Now let's talk about something called the R-squared value. Okay, so we found a relationship between age and BPF, but we haven't talked about how well our model fits the data. So we said that as age goes up, BPF goes down, but how well does our model fit the data? So there's this thing called R-squared, okay, which is called sometimes the coefficient of determination. And it's the proportion of variance or variability in the outcome explained by the model. So in our example, we know that BPF for different people varies, but what R-squared tells us is the amount of the variation in BPF that we can explain with a patient's age, okay? And so when we have one predictor, as we do in this case, the R-squared value is simply equal to the total sum of squared minus the error sum of squares divided by the total sum of squares, okay? So this will make a lot more sense with some examples, okay? So just thinking conceptually about this, what if all the variability in the outcome was explained by the covariate? In this case, R-squared would be equal to 1, right? And then what if none of the variability in the outcome was explained by the covariate? Then R-squared would be equal to 0, okay? All right, so let's take a look. It turns out this is already a part of our Stata output. We just hadn't been looking at it specifically. Okay, so here's our same regress, BPF, and age. And the sum of squares are here. And then here, you'll see this R-squared value, which in this particular case, the R-squared is equal to 0.3330, okay? And so how does the R-squared value compare to R, which was Pearson's correlation coefficient? Well, as you might have guessed, R-squared value is just Pearson's correlation squared, R-squared, little r-squared, okay? And before we had said that R is always going to be between -1 and 1, okay? And so as a result, when you square a number that is between -1 and 1, you'll always get a smaller number. So R-squared is always less than R. Less than or equal to R, we should say. Less than or equal in the special case that it's equal to 1. Okay? So in our particular example, we had these values. Here was Pearson's correlation, -0.577, and then the R-squared value of 0.33, okay? All right, so that's the amount of variability. So we can say that age explains 33.3% of the variability in BPF, and that's a very cool result, right? So we know BPF varies for different people, but if we know that person's age, we can predict 33% of the variability. A very neat result. Okay. Now let's talk a little bit about prediction. Okay. So we've determined that there is a significant association, but we can also use linear regression to make predictions. Okay. So using the regression equation, we can get predicted BPF for patients with specific age values. Let me say that again. Using the regression equation, we can predict the BPF for patients with specific age values. Okay? So let's take an example. Suppose a patient is 40 years old. We can plug that into our regression equation to get a predicted BPF for that patient. Okay, what would that look like? Okay, so here's our estimated intercept, here's our estimated slope. Now we're saying that the patient is 40 years old, so we just plugged all that into our regression equation, and we get an estimated BPF for that 40-year-old patient is 0.841. Okay, that's the expected BPF, or the mean BPF for a patient age 40. Okay, but one thing we have to be careful about is to avoid extrapolation. What do we mean by that? Okay, so the data that we had that we used to fit this regression was here. Okay, looks like we had data on people from around age 20 to up to age 60. Okay, and so when we say avoid extrapolation, what we mean by that is, since we only had people between age 20 and 60, we shouldn't be making predictions for people age 70 or 80, for example, because we have no data there. Okay, or for kids, 10 or 15 years old. Okay, we only want to make predictions in the range that we collected data. So here between 20 and 60. Okay, so avoid extrapolation. Okay, so just like before, we can put a confidence interval around our predicted mean value. Okay, so that corresponds to plausible values for the mean BPF at a specific age. Okay, so if we want a confidence interval for a mean value. Okay, these are plausible values for the mean BPF. Again, mean is a key word here. The mean BPF at specific ages. Okay, and in order to get these confidence intervals, you guessed it, we need an estimate of the variability or standard error. Okay, and again, we'll leave the determination of that to the statisticians, but we can use the results to inform what we do. So here's the standard error of y hat. It's this formula here. And so given that, we can construct a confidence interval. Okay? And you'll notice that the standard error equation here has different magnitude based on the x value, right? Because of this term. That changes with the x value. So in our example, it changes with age. In particular, the magnitude is least when x equals the mean of x. Okay? So in other words, our variability is going to be smallest for the people in the middle of our range. Remember, we had people from age 20 to age 60. So our variability is going to be smallest for the people right around age 40. Okay? And this is based on a t-distribution again. And so we can write out what this would look like. Here's our familiar format. Estimate minus critical value times standard error, comma, estimate plus critical value times standard error. Okay? So what does a picture look like? So let me get rid of this. Here. Okay, so the red represents our fitted regression equation, where the green and yellow or orange represent our confidence interval around that. And just like we mentioned, the confidence interval is tightest in the middle, right around age 40, because we're most sure about this area. We have plenty of data here, we have data to the left, we have data to the right, and so we're most sure about this stuff in the middle, okay? Which is why these lines kind of curve inward, okay? So that's our confidence interval, okay? So a confidence interval for the mean provides information regarding the accuracy of the estimated mean value for our particular data set, okay? So that's the mean value. Remember, we always said, here's the confidence interval for the mean BPF, okay? But instead, we might be interested in how accurate our prediction would be for a single observation, not for the mean of a group of observations, okay? So this is called the prediction interval, okay? So what would you estimate as the value for a new single observation, okay? So this is a bit different. Before we were saying, what's the mean BPF for a certain age? Now we're saying, suppose somebody's 40, what is their estimated BPF, okay? So do you think a prediction interval is narrower or wider than the confidence intervals that we were looking at before, right? Well, obviously it's going to be wider. And the reason for that is the variability in the prediction of a single observation, okay? Let me just write that out. Prediction intervals are always wider than confidence intervals, okay? And the reason for that is that the variability in prediction of a single observation as opposed to the mean as opposed to the mean contains two types of variability. One is the variability of the estimate of the mean, which comes through in the confidence interval. And then there's the second type, which is a single person's variability around the estimate of the mean. Okay? So that's sometimes called the residual variability. Residual. Okay? So what does that look like? So if we were to write that out, it would take on the following form. Okay? So here's a standard error for a predicted person. Okay? And you can see it involves both the variability of the estimate of the mean, which we had before, and also the variability around the estimate of the mean. Okay? And so if we were to construct a confidence interval, again, it would take this familiar format of the estimate minus the critical value times the standard error, comma, estimate plus critical value times the standard error. Okay? And so if we were to add the prediction interval, here's the picture now. Here's our fitted regression equation. Here's the confidence interval, the green and the orange, for the mean. And now these outer estimates are the prediction intervals for a single observation. Okay? So hopefully that makes sense. Basically what we're saying here with the green and orange is here's a confidence interval for the mean, but we know individuals are going to vary more than that. And so that's the prediction interval with the outermost intervals. Okay? So our conclusions are that prediction intervals are always wider than the confidence interval. Okay? And it's common that we can find significant differences between the means of groups, but we can't predict very accurately. Okay? All right, so that wraps up our introduction to regression. Going forward, we're going to talk a little bit more about regression diagnostics, and what we mean by that is how can we assess those 4 assumptions that we need in order to fit linear regressions. And then we're going to talk about a further discussion about how to interpret these linear regression coefficients, because the interpretation of their coefficients is what's essential for medical research. Okay? All right, so I will stop there, and I will see you in the next session.